Okay, this is still section 4.2. It's just a specific type of a problem that makes use of the compound events and all this. Well, it's not obviously, but it's going to make use of the multiplication rule, probability of this happening and that happening. Special types of problems. Anyways, going back to the beginning of 4, when we know this, the probability of something happening, probability of A plus the probability of the complement of A equals 1. Something's going to happen. Either it rains tonight or it doesn't rain tonight. Either I get an A in the class or I don't get an A in the class. The probability of something happening plus the probability of the complement of that thing happening is equal to 1. It's a sure thing. Something's going to happen, one or the other. Now, doing a little bit of algebra, we can figure out that the probability of something happening is 1 minus the probability it doesn't happen. And like manner, the probability of something not happening is equal to 1 minus the probability that that event did occur. All right, so basic. What we're going to do is make use of this guy right here. We're going to be trying to calculate the probability of at least one thing happening. We're going to do it by what's called the complement rule. Probability of something happening is 1 minus the probability that it did not occur. All right. Many times in probability or just in mathematics, it's easier to solve the problem sort of coming in the back away from reverse. Right. So we know this. The probability of me rolling a 4 is 1 chance in 6, and the probability of not rolling a 4 is 5 chances out of 6 because there's 5 numbers on a die that are not the number 4. Hey, the sum of these guys equals 1. One of these two things is going to happen. The sum of the probabilities is going to be a sure thing 1. If you know the probability of an event happening is zero point 0.7, then you know the probability of the event not happening is 1 minus 0.7, 0.3. And like math, the probability of something happening is 0.15, then the probability that it doesn't happen is 0.85. In a like manner, if you're told that the probability of something not happening is 0.85, then you know the probability of something happening is 1 minus 0.85 or 0.15. It's a handy little rule, and we're going to make use of it in this next section. All right. This set of problems makes use of the complement rule. What he tells us is that we're going to, really study this in chapter 5, which we're not there yet. But there we'll study probabilities associated with what's called binomial experiments. Binomial experiments have two outcomes, a success and a failure. One feature of these experiments is that the outcomes can be categorized by the number of successes out of independent trials. If you have a simple event in a sample space, you could have 0, 1, 2, 3, 4, all the way up to n successes. Here's the key thing to this whole section here. A convenient way to compute the probability of at least one success is to observe the complement of at least one success is 0 successes. Then by the complement rule, to calculate the probability of at least one success is to take the whole number 1, subtract the probability of 0 successes. All right. So let's see. Let me just move this out of the way. Very important. The complement of at least one is none. 0. All right. Complement of at least one is none. All right. So probability of at least one is at least one. Let's solve the following problem. Let's assume we got 5 kids. All right. And we want to find a probability of at least one of these kids attending Brockton schools. All right. There's my 5 kids. Diverse group, as you can see. At least one is equivalent to one or more. At least one means, hey, it could be one kid goes to Brockton schools, 2 kids, 3 kids, 4 kids, 5 kids. Perhaps there's only one kid that goes to Brockton. Problem is, though, is it the first child, Brenda, or is it Kathy, the second child, or is it Karen, or is it Steve, or is it Raphael? Well, maybe at least one means that there's 2 kids. At least one means one or more, or up to 2 kids. Problem is, I don't know if it's Brenda and Kathy, or maybe it's Brenda and Karen, or Brenda and Steve, or perhaps it's Brenda and Raphael. You see the problem this presents, all right? We will study this in section chapter 5. See, right now we don't know how to find a probability of exactly 1 or exactly 2 or exactly 3. So to solve this at least one problem, we're going to be making the use of the complement rule because we know the complement of at least 1 is none. None of the kids, none of the 5 kids go wrong. All right, so here's the process here. This problem is just suppose we want to find a probability among 3 children there's at least 1 girl. In such cases, the meaning of the language must be clearly understood. At least 1 is equivalent to 1 or more. The complement of getting at least 1 of a particular type is you get none of that type, no items of that type. For example, not getting at least 1 girl among 3 children is equivalent to getting no girls, which means all 3 kids were boys. The way we set it up is this. We use the symbol A to denote getting at least 1. We let the complement of A bar here, represent the event of getting none of the items being considered. We calculate the probability of none of the outcomes resulting in the event being considered, and then we take that and we subtract it from 1. We use this complement rule. All right, so because we have 5 kids to consider, constructing a sample space is a tedious task. We don't know if it's exactly 1 or exactly 2 or exactly 3 or 4 or 5. So we're going to use this complement rule. Probability of getting at least 1 kid going to Brockton is 1 minus the probability that none of the 5 go to Brockton schools. Let's assume, just for an argument's sake, that the probability of a child attending Brockton is 0.8. Therefore, the probability of not attending Brockton schools is 1 minus 0.8 or 0.2. It's arbitrary numbers that I chose. Probability, we're looking for the probability of at least 1 kid attending Brockton schools. How we're going to solve this is take the whole number 1, subtract the probability of none of the 5. The complement of at least 1 is none. None of the 5 going to Brockton schools. So it's 1 minus the first child doesn't attend Brockton schools, and the second doesn't, and the third doesn't, and the fourth doesn't, and the 5th kid doesn't go to Brockton schools. Well, we know the probability of not attending Brockton schools is 0.2. These are purely independent events. In other words, I don't have to adjust the probability of the second, third, fourth, and 5th kid because the fact that 1 kid doesn't go does not affect the fact that another kid doesn't go. Purely independent. So these probabilities are remaining constant. So what we see here is 1 times 0.2 raised to the 5th power. Doing this with my calculator, I get this decimal 0.99968. Defective Firestone tires. Assume the probability of a defective tire is 0.0003. Well, already I'm thinking to myself, the probability of a defective one is 0.0003. The probability of getting a good tire must be 1 minus that, or 0.9997. See, it doesn't tell us that, but we're going to be smart enough to say, hey, if we know the probability of a defective one, chances are we need to know the probability of getting a good one. All right, so he says, hey, find a probability that at least one of these 100 tires is defective. Well, that could be 1 tire is defective, 2, 3, 4, 38, 49. Tired already. So the easy way around this is to use the complement rule. All right. Let's first let A be the probability. Let A equal at least one of the 100 tires is defective. Identify the complement. The complement of at least 1 defective is you get none of these defective. None of them are defective means all 100 must be good. That's a good one and a good one and a good one and a good one. All right. So here again, this problem represents a independent event because getting a good tire or a bad tire has no effect on the second and the third. So all 100 are good. So the first one is good, and the second and the third. So it's an and situation. So I know I'm multiplying. But once I get this, I have to remember I got to subtract this from the whole number 1. So taking 0.9997 and multiplying it by itself 100 times is like taking that number, raising it to the 100th power, but remembering now I've got to subtract from 100. And what you'll see on these, if you see a problem like this on the exam, this answer will probably be A, and people fall for that, not remembering that they had to take this and subtract it from 1 to get the complement. 0.0296. An unprepared student makes random guesses on 10 true or false questions. Find the probability at least one answer is correct. Well, at least one could be one or two or three or four, all the way up to how many questions? 10, right? So I don't know how to find exactly one or five or seven or eight. So I'll use the complement rule. Probability of at least one correct is one minus the probability that none were correct. Well, if none were correct, it means that they all are wrong. Well, probability of getting it right is zero point 0.5. Probability of getting it wrong is also zero point 0.5. So it's one minus the first one was wrong, and the second one was wrong, and the third one, well, it's zero point 0.5 times itself 10 times. Now, this is an and problem because this one was wrong and, which means multiply. The other second one was wrong and the third one and multiply. So 1 minus zero point 0.5 to the 10th power, your calculator gives me 0.999. So the probability of getting at least one question right and 10 false questions is pretty high. Just by guessing. Just by guessing. Batch of 8,000 radios, 5,000, I'm sorry, 5% are defective. Well, before I go any further, 10% of 8,000 is 800. 5% would be 400. He's not telling me this, but it's a good chance I'm going to need that somewhere. If I've got 400 that are defective, it must mean I got 7,600 that are good. This is the part that you got to do your thinking on. He'll give you the information, but sometimes you got to go digging for what it is you need. A sample of 14 clocks is randomly selected without replacing the 8,000. The entire batch will be rejected if at least one of those testers is defective. What's the probability that the batch will be rejected? Meaning, what's the probability that at least one is defective? All right. Now, recall back in 4.1, if things get to be cumbersome, even though these things are independent, sometimes, I'm sorry, dependent, even though these guys are dependent, meaning, hey, I pull a bad radio out, then I've only got one less radio. I pull another one out, I got one less bad one and one less total. This problem represents something that is dependent, but I don't want to do this 14 times. All right, so I want to treat this as being independent. In actuality, it's a dependent situation. All right, so probability of getting at least one defective is one minus probability that none are defective. Well, what does it mean to be none are defective? It means all 14 must have been free of defects. It must have been they're all good clock radios. Well, 5% of the 8,000 are defective, therefore you've got 7,600 good radios. All right, so probably of me getting a good radio is 7,600 over 8,000. But I'm doing this 14 times. All right, so it's 1 minus 7,600 over 8,000 raised to the 14th power. All right, and the calculator does this. You put this into your calculator, it'll give you, making sure you enclose this division portion in parentheses raised to the 14th power. All right, so these at least one problem, make use of the complement rule. Many times you got to go digging for all the information. He'll give it to you. He'll give you enough information to figure out what you need, but you got to go. You got to use your head, ladies and gentlemen. All right, you got to use. I'm going to give you these 5 problems again in a PDF so you can work on them your own. I would say this: work it out, and then come back to this PowerPoint and see how they were solved. You're going to see at least one problem on chapter 4 exam. So I'm taking the time. Special application of the and situation. Probably of this happening first and that happening second, and so forth. At least one, and then we'll study this in depth when we get to binomial probabilities in chapter 5. So you can see we've come a long way from finding the mean, even box plots. But I told you this would happen. I hope you didn't think it was going to be more chapters 1, 2, and 3 for the rest of the course. No, it's a little more challenging.